Hello, chemistry students. Today we are going to talk about limiting reagents and percent yield. By the end of this video, you should be able to explain how the amount of product in a reaction is affected by an insufficient quantity of any of the reactants, and be able to explain what the percent yield of a reaction measures. So let's start with limiting reagent. The limiting reagent is the reactant that determines the amount of product that can be formed by a reaction. Okay, so the reaction will stop when you run out of the limiting reagent. The other reactant, the one that is not completely used up, is called the excess reagent. For example, let's go back to our cookie example from last time, okay? In this example, you have everything you need in your pantry, and you're going to make as many sugar cookies as possible. You have more than enough of most ingredients, but you only have 2 teaspoons of baking soda and 3 cups of butter. So how many cookies can you bake? Which ingredient is the limiting reagent and which ingredient is the excess reagent? Here we have our balanced equation. So when you're figuring out what is the limiting reagent, you actually have to do the calculation 2 times. So we will start with the butter. For every 1 cup of butter, you can make 48 cookies. So when you finish this calculation, you find that you have enough butter to make 144 cookies. Now you need to do the calculation using the other reagent. For every 1 teaspoon of baking soda, you can make 48 cookies. So you have enough baking soda to make 96 cookies. After you complete this calculation, or maybe before, you can see that the limiting reagent is the baking soda, and the excess reagent is butter. Okay, let's practice with some atoms and molecules. The balanced equation for the reaction of copper with sulfur to form copper 1 sulfide is as follows. And they want to know what is the limiting reagent when 80 grams of copper reacts with 25 grams of sulfur. So this is just the same. Our starting values are 80 and 25. And we need to do the calculation 2 times. The molar mass of copper is 63.5 grams per mole. And from the balanced equation, you can see that it takes 2 moles of copper to form 1 mole of copper 1 sulfide. Now, you don't have to convert copper 1 sulfide into grams. We can just compare the moles of copper 1 sulfide that are expected from 80 grams of copper to the moles that are expected from 25 grams of sulfur. Let's check our dimensional analysis. Grams of copper and moles of copper go away. We're left with moles of copper 2 sulfide. When you complete the math, you get 0.6299 moles of copper 1 sulfide. Okay, so let's compare that to how much copper 1 sulfide we can expect from 25 grams of sulfur. The molar mass of sulfur is 32.1 grams per mole. And it is a 1-to-1 molar ratio from the balanced equation. That comes out to 25.0 divided by 32.1. Let's check our units. Those cancel, and we're left with the same unit as above. Moles of copper 1 sulfide. Okay, so when you divide those two numbers, you get 0.7788 moles. Awesome. So when you look at those, you can use that to answer the question in the form of a sentence. You can say copper is the limiting reagent. The equation for the complete combustion of ethylene is as follows, and thankfully it's balanced. Identify the limiting reagent when 2.7 moles of ethylene reacts with 6.3 moles of oxygen. Okay, so they gave us the amount of this reagent we're starting with and the amount of this reagent that we are starting with, and they want to know which one of them will run out first, which one is the limiting reagent. Now, the nice thing about this problem is they gave us the starting number already in moles, so we don't have to use molar mass to convert it. We can just go straight from the known value into the molar ratio. So it looks like it takes 1 mole of ethylene, and we're going to have to just choose one of the two final products to go with. So let's just use water for both equations. And so it takes 1 mole of ethylene to produce 2 moles of water. That will come out to 5.4 moles of water. Now again, we are already in the unit of moles, so we can just use the molar ratio from the balanced equation as our next step. It takes 3 moles of oxygen to produce 2 moles of water. So that gives us 12.6 on the top and 3 on the bottom, which comes out to 4.2 moles of water. Comparing those two numbers, you can see that oxygen is the limiting reagent. You should be feeling pretty comfortable with these stoichiometry calculations by this point. So we're going to throw some new vocabulary words in there. Chemists use balanced chemical equations just like you've been doing, and those numbers that you've been calculating are actually called the theoretical yield. So this is the maximum amount of product that can be formed. But the actual yield is the amount of product that is produced in the laboratory. So we've got the theoretical yield and then the actual yield. Let's go back to our cookie example for just a second. Think about it. If you're making 48 cookies from those ingredients, you might come up a little shy when you're actually baking the cookies. There might be some dough that's stuck to the dough hook or the bowl that you couldn't get on the cookie sheet. Or there might be another thing that goes wrong. You might burn some of the cookies. So the actual amount of cookies that you produce might not be 48. Theoretically, you should be able to make 48 cookies, but in actuality, it might be less. You use those numbers, the theoretical yield and the actual yield, to calculate the percent yield for a reaction. So that's the ratio of actual yield to theoretical yield represented as a percentage. Here, you're going to want to put this down in your notes. This is the percent yield formula. Okay, so we're going to use that formula in the next couple of examples. When 84.8 grams of iron-3 oxide reacts with an excess of carbon monoxide, iron is produced. What is the theoretical yield of iron? So in this one, we're not calculating the percent yield quite yet. We are just practicing the theoretical yield one more time. Now, let's look at this. They gave us the number 84.8 grams of iron-3 oxide. So that one is right here. That's the thing we're going to start with, and it is in the value of mass. And it also tells us some interesting information here. It says excess of carbon monoxide. So when you see a sentence like this in a question, basically that is telling you that iron-3 oxide is the limiting reagent. Okay, so you don't have to figure out what the limiting reagent, with this little phrase, they just told you it's iron-3 oxide. So we're only going to have to do it one time, and then they want to know how much iron is produced. So we're going to give them that answer in grams. Okay, so molar mass of iron is 55.8 grams per mole. Oxygen is 16 grams per mole. So iron-3 oxide, or Fe2O3, is equal to 159.6 grams per mole. From the balanced equation, we see that for every 1 mole of iron-3 oxide, you produce 2 moles of iron the molar mass of iron 55.8 grams per 1 mole. Okay, so this stoichiometry calculation will show us the theoretical yield of iron. Let's check our units. Make sure they all cancel properly, and that we're left with a mass of iron. And then we're going to multiply everything across the top and bottom, which will give us 9,463.68 and 159.6. So my calculator tells me that that is 59.296, and our significant digits should be 3, so that's 1, 2, 3, and 9 will actually bump 2 up. So your final answer is 59.3 grams of iron. That is the theoretical yield. All right, on this last example, we're going to throw it all together and we're going to find the percent yield of silicon carbide. Okay. If 50 grams of silicon dioxide is heated with an excess of carbon, 27.9 grams of silicon carbide is produced. What is the percent yield of this reaction? Okay, so let's break this down. They tell us that there's 50 grams of silicon dioxide. That's our starting number. It lets us know that there's an excess of carbon. Okay, so what does that tell you? Alrighty, so what is the percent yield of this reaction? Oh, look, there's one more thing that we know. It says that 27.9 grams of silicon carbide is produced. So the actual yield is equal to 27.9 grams of silicon carbide. Now we just need to calculate the theoretical yield if we start with 50 grams of silicon dioxide. So the molecular mass of silicon dioxide is 60.1 grams for every 1 mole. The molar ratio is a 1:1. And the molecular mass of silicon carbide is 40.1 grams per 1 mole. So when you multiply everything on the top and everything on the bottom, you will end up with 2005 divided by 60.1. Checking our units. And then finishing the math. Okay, so this gives 33.36, but I can only use 3 significant figures, so 1, 2, 3, 6 will actually affect that. And our final answer is 33.4 grams is equal to the theoretical yield. So how did this chemistry student do? in their experiment. How much product did they lose? That is where the percent yield calculation comes in. So percent yield is equal to 27.9 divided by 33.4 times 100%. They were able to produce 83.5% of the maximum amount of silicon carbide.